Raspberry Pi time. This time, not talking about a Raspberry Pi Zero wireless, like I've been talking about for the thermostat project. This is a Raspberry Pi 4. I was interested as I got involved a few months ago with the Rosetta at Home project, but primarily I wanted to focus on the transition that I was making from using all of my computers and transitioning to something that I could donate compute time with long term. So I wanted something to be low power and efficient, check. Inexpensive, check. Fast, we'll get to that, but I would say check. Modular, and with low thermal dissipation. So the amount of heat coming off of the thing relative to its performance is low. And that could probably be considered the same as efficiency, but I think it's important to delineate between the two when we're talking about what additional power outside of the central processing unit, the CPU, or the graphics processing unit, the GPU, RAM, or other parts of the system that require active cooling, a fan, water cooling, radiators, pumps, things like that, to keep the whole system cool, and how much power goes to just being used to keeping the system cool as opposed to just using an efficient system that doesn't need a lot of active cooling. So after looking at a variety of different computing devices, like the Intel NUC, some Mac Minis, and other small form factor PCs that I could build, kind of came back to really wanting to see if I could find a way to make the Raspberry Pi 4 work, because it just ticked all the boxes for how efficient and how fast it was, and again, low cost and low thermal dissipation. The project that I was contributing to, Rosetta at Home, about a month ago announced support for the ARM64 architecture, and that pretty much sealed the deal for me. So I bought one of these just to test out what the performance would be like, because there wasn't much information on it. There were a plethora of videos and things out there talking about how fast it could run certain benchmark, how much faster it was than the Raspberry Pi 3 and 2, and it left the question of what desktop processor is it comparable to? Because we haven't seen this sort of thing, especially at such a low price, for $55 just for the single computing board itself. We haven't seen something like this that is powerful, if not more powerful, than some low to mid level mobile and desktop processors. I thought I would just walk through the Raspberry Pi 4 real quick and give kind of a tour of some of the things that are going on with it and the kit that I bought. So the thing you're seeing wrapped around it is the heavy-duty aluminum alloy case with fan from Vilros. And this comes with it says right here, with fan. So there's the fan. And the fan plugs into this header that has both 5 and 3.3 volt available, and you can choose whether or not you want to use 5 or 3.3 volts. The fan has a little controller in it that prevents you from reverse wiring it, so that's a nice little protection feature they built into the fan. So if you get this kit, set it up, plug things in backwards, happens, and the fan doesn't turn on. If you're not, make sure your connections are right, because it will not go in the opposite direction. And the reason why I tested this was not because I miswired it, which certainly I've done my fair share of miswirings and to fantastic results. But no, I was trying to see if I could reverse the flow of the fan, because I wasn't exactly sure if I liked the fact that it was exhausting out the top. I was kind of preferring that it would draw air in this way and push it out the side. But having messed around with it and getting the fan on this side and then being able to push air through it, no, it's much more efficient at drawing air away. Clearly they thought this thing through, and it works better with it drawing air away from the hot thing as opposed to pushing air down on the hot thing. The fan is really quiet. It runs, like I said, at 5 or 3.3 volts. At 3.3 volts, it really doesn't move enough air to keep the CPU below its thermal threshold. But with it at its 5 volt speed, it's still pretty quiet and keeps the CPU at about 65 degrees Celsius to around 70 at 1.9 gigahertz overclock and a 550 megahertz overclock on the GPU. As far as the Raspberry Pi itself, and there it is. It's got the 2 heat sinks on it that came with the Vilros kit. I don't think they have I think the box. Oh, the heat sinks came in the box here. Yeah, it says heat sinks inside. So heat sinks came in the box. They give you a little card to tell you how to choose between pin 1 for quiet mode or pin 2 for full power. It's just a 5 volt or 3.3 volt rail. They choose pin 14 as the common, the return. I don't know. I just use pin 3 or pin 4. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, I use pin 4. Sorry. No. I use pin 6. Pin 4 is also the 5 volt rail, so don't use pin 4. You'll be putting 5 volts across both sides of the fan. So the heat sinks are nice. It's nice to have one for the RAM. There are some kits out there that have heat sinks for the USB controller and the Ethernet controller, but I don't see the need for that. The USB controller was getting hot in earlier firmware builds for the Raspberry Pi, but it appears that's been rectified, and even overclocking this hasn't resulted in any sort of issue that I've seen, but there are no things that are plugged in via USB. So I might do additional testing with something plugged in on either the USB 2.0 or 3.0 ports to see if that changes anything. But so far, even with an infrared thermometer, I haven't seen temperatures rise super high. The case fits together quite nicely. It has 2 slots that it's used to draw air in. One that's drawing air primarily over the CPU and the RAM, and the other that seems to be over the power controller circuitry over here. Or, yeah, it seems like it's kind of over here. Seems to keep it cool enough. The system does get unstable at 2 gigahertz and 2.1 gigahertz, so the things that on some of the blogs that I've been talking about overclocking up to 2.1, at least in this enclosure and this configuration, it's not stable after a few minutes. So I'm investigating that, and probably will post further videos on that as we go along here. One thing I would note about the enclosure is that since it is metal, there are 2 features here that hold the Raspberry Pi in place, and then there are the 2 screw holes on the bottom. So when you're screwing this together, there are 4 screws that go in here, and it's important to not over tighten these screws. They do send a screwdriver, a right angle screwdriver, so that you can use it with the screws they provided. I don't particularly like this, but I do see why they supplied it, because it helps prevent you from over torquing the screws, but I just use my regular screwdrivers. Just make sure you don't over torque it, because you don't want to crack the multi-layer board. Overall, the case is good. It's well built. It allows you to see the indicators, access to all the peripherals. The kit also comes with a mini HDMI to HDMI adapter, which I don't have in front of me, but it comes with one. And that's helpful because I didn't have any of them. So it was nice to have one. Finally, the power supply is well done. They supply it with a 5.1 volt, 3 amp USB-C supply. It comes with an inline switch, so it's kind of helpful when you're needing to reset. And it is rated accurately. So this has been able to, with some modifications, able to get this up to 2.15 gigahertz at a 550 megahertz overclock on the GPU, which I will talk about in a separate video, using this adapter. And that power consumption is around 11 to 12 watts, so you're starting to get really close to the maximum output of this supply. And I was a little bit concerned that it would be fine for the base configuration at 1.5 gigahertz, that's drawing maybe 6 watts. And then the 1.9 gigahertz configuration, which is 8 watts. But then up to the maximum I could get it to with some little hand wavy magic, the stock supply still was able to power it without any hiccups for 2 days. So usually these switch mode power supplies, if they get too hot internally, it'll just fold back or cut off, and it did not do either of those things. So it doesn't take a long period of time to get a good test of how the supply is behaving. More on that in a future video, but safe to say this is a good supply that comes with it. So for the whole kit, it's nice that it's a robust power supply. The only things that I've experienced that I would say are less than optimal with the Vilros kit is that the amount of airflow from this fan seems to perhaps be limiting the performance that you can get out of this whole system. And I would have preferred a fan with a little bit more velocity, a little more air movement through it. But like I said, you are able to get a very consistent overclock, and it's been running for a month. You can tell by the dust that's accumulating on the fan there that it's been running for a little while. To finish off the hardware setup, I had to pick an SD card. And for the Raspberry Pi Zeros, the ones I would go for are pretty much always the SanDisk, just the basic SanDisk cards, or the Samsung Evo 32 gigabyte Evo Select. These are fine. If you have a bunch of these and you don't really care, how long they last, they're fine. But what I opted for was a bit more of a robust card, which is this SanDisk high endurance 128 gigabyte card. But this specifically states that it's designed for continuous recording. So it says up to 10,000 hours of continuous video recording. So this thing can be recorded at 3.2 megabytes per second, 24/7, 365 for 1.14 years. And the Rosetta at Home project does make use of a significant amount of disk I/O and some disk storage for a particular work unit. So one unit of work, to which this particular system with having 4 cores can run up to 4 work units. I've noticed from work on other computers, as I've looked across all those machines, the average amount of data being written and read to the permanent storage device is somewhere in the vicinity of 5 gigabytes per processor core per day. So in the case of this Raspberry Pi, it would be 4 cores, so it'd be somewhere in the vicinity of around 20 gigabytes per day. In the case of a 6-core, 12-thread Intel Core i7, that would be somewhere in the vicinity of upwards of 60 gigabytes a day. Now, more recent versions of Rosetta, that's the Rosetta at Home application, have reduced that to around, at least on the machine that I have, that has 12 threads, has been reduced down to around 40 gigabytes per day. Safe it to say, it does make use of a lot of disk I/O and disk storage. When it comes to a SD card or a solid state drive, they have finite write cycles, and it's something that I've paid a little more attention to and looked for something that is going to be able to be used with high amounts of disk writes and will run as long as it possibly can without failure. So SanDisk high endurance card 128 gigabyte is what I end up going with, and so far 1 month in, going pretty good, and we'll see how it goes longer term. Before we get into any steps of configuring this, I thought I would talk a bit about the performance of this after about a month, and I've had 3 of them running now, this and 2 others, and contrast that with some other computing platforms that I have or we have on our team to give an indication of how performant this is, and more importantly, the performance per watt for this computing device as compared to other things that are out there that might be a couple years old, that are computers you'd find in your basement or something like that and want to use to contribute to projects like Rosetta at Home. So the one system my friend has is a Core i5 second generation operating at 2.6 gigahertz, and it overclocks to around 2.9 gigahertz. It has 8 gigabytes of RAM, and it has a solid state drive. It generates running 24/7. All these machines are running 24/7, not 365 because we haven't gone a full year yet, but at least these have all gone at least 1 month continuously. So we'll say for at least 30 days. And that's the same for all of these. It's generating an average of about 1,700 recent average credits and uses 40 watts. So its performance per watt is 42.5 performance per watt. The 6-year-old Core i5 4th gen operating at 1.4 gigahertz with 4 gigabytes of RAM and a solid state drive generates around 2,100 recent average credits. So that divided by 25 watts is what it averages around, is 84 performance per watt. The Raspberry Pi generates 1,200 recent average credit at 8 watts. And we do the math on that, 150 performance per watt. So this, compared to a machine that is 9 years old, this is 3.52 times more efficient. And then compared to the 6-year-old machine, 1.78, almost 1.8. To kind of frame this out, the reason why I'm talking about all this is that power, especially when you're donating computer resources, is that this power may still seem low. 40 watts, 25 watts, 8 watts. It's not crazy high amount of power. But if it's something that you're looking to donate continuously, which is what I started off talking about, these start to add up. And I'm talking about low power chips. These are lower power chips, not desktop 65 watt or 130 watt TDP chips that could really add up, that may not be that much more performant than this Raspberry Pi 4. And again, I'm thinking of older machines that you might find in, like you might have in your garage or something like that. That's like even Intel Core Duo chips or Core 2 Duo chips that might run in 64-bit mode and be able to get you into a modern operating system, I think, but are not going to come close to the performance per watt of something like this, like a single board computer like this. Just to kind of frame that out, I'm going to look at total cost over a year, and we'll just do a quick calculation of running these things 24/7, 365, and what the cost would be in a given year. So if I'm looking at this 9-year-old Core i5, modestly rated 40 watt machine, if I do 40 watts times 24 for a day, let's do it in kilowatts. So 40 divided by 1000, 0.04 divided by 24 for 1 day, divided by 365 would get us to 350 kilowatts per year. The average cost of electricity in the US is 14.1 cents per kilowatt hour, so we'll just round that down to 14 cents. And this one would cost $49.05 per year. The 6-year-old Core i5 4th gen running at a lower clock frequency, but running at 25 watts, if it were running continuously, 219 kilowatts per year times 0.14 would get us to $30.66 per year. Finally, our little Raspberry Pi 4 running at 8 watts, $9.81 per year. So for the amount of money that you would save between these two, and let's say you run it for 2 years continuously, this would be $100, this would be just under 20. It's $80. It's basically the cost of a second Raspberry Pi. So you could buy 2 of them and get around 2,400 recent average credits, which would be faster than both of these machines, while still using $20 a year to $30.66 a year. So you'd still be saving $10 a year operating with 2 of these. And I actually have 3 of them, so they're around 3,600 recent average credit for 3 of them, and I might add a 4th one actually, because again, they're just so efficient. And this is all operating at a conservative overclock of 1.9 gigahertz. I will note that this method of scoring, it varies. I took the low end of all of these things. I took the lowest I could find for all of these things over time. Sometimes this would peak around 2,200, 2,300. Again, this would come up to around 2,000. This is what varied the most. The average that I got over 30 days was around 1,200, but support for the Raspberry Pi 4 is new. There were days and stretches of several days where I saw the performance go between 1,400 and up to 1,900 recent average credits. As far as performance, this has the potential to be more performant than a 9-year-old machine drawing 40 watts. And even faster than a 6-year-old machine that's drawing 25 watts. And if you were to bring it to watt parity, talking about performance per watt, the Raspberry Pi 4 with that ARM Cortex, I think it's version 8. I'll correct myself, I may be getting this totally wrong. But that architecture and construction is just way more efficient than a lot of low to mid performant computers. If you're looking at a used computer machine that's been sitting in your garage or in your basement, you go like, oh, that's several years old and I'd like to just use that for this project, I would think about perhaps recycling that computer or taking whatever parts you can take out of it, maybe selling those parts, and then buying yourself a Raspberry Pi and using it as the compute platform, because its performance is really quite impressive. Okay, so now that you're all excited about the Raspberry Pi 4 and are going to go run out and buy a baker's dozen of them, the next video will focus on getting this thing set up. I will be walking through setting up the operating system. In this case, it'll be Ubuntu 20.04, but I'll be talking about other operating systems too that you can use to configure this and run BOINC and Rosetta at Home. And I'll also talk about other projects that are out there as well. One video that I will be doing that'll follow the next one will be one about performance tweaks and really getting into the nitty-gritty of things that I've learned and how to get the most performance out of this awesome single board computer. So like and subscribe. Go get your Raspberry Pi 4s or go find the ones that you already have. And let's get going to building this thing up and getting it running to help with Rosetta at Home or any project that you want to donate compute time to in the next video. Till then, take care.